Okay, so we are going to start the next unit. This unit is going to look at the tail end of chapter 5, and then I'm skipping all the way into chapter 16. So I'm kind of bouncing around in the textbook. We are going to be studying the field forces. So in physics, the field forces, just as a reminder, are forces that act over a distance. They do not involve physical contact. So field forces are actually the fundamental forces that describe how our universe works. There are four fundamental field forces, and there are other ones that are being discussed, very high level stuff. But we're going to focus in on two of those. So the first field force is the first one to be mathematically quantified, and that is the force of gravity. And then the other field force that we'll get into in chapter 16 as the force of electricity, and then we'll talk a little bit about magnetism. So we'll start with gravity. And gravity is, like probably the force in nature you first heard about as a kid. And so I think because we use it so much, every single physics problem we've done so far, it's the only force that has been in every single free body diagram you've drawn. You've put it as mg up until now. So it's a force that we just sort of like take for granted, right? We started talking about it right away with how objects fall when we did our vertical motion problems. Galileo figured out the 9.8 value that we use as our acceleration due to gravity. Newton, who we're going to discuss today, he was the first person to really get into field force and try and figure out an equation for it. And his equation still holds true. But all of that being said, gravity is one of the most mysterious things in physics right now. There's a lot of work being done with gravity and how it works. So with this unit, we're going to, I'm super bummed I can't do it with you because I geek out over this stuff. But we're going to try to do some virtual modern physics towards the end of this week and into next week. So we'll start just with Newton's version of universal gravitation because it is still correct. But Einstein actually did some of the greatest work with gravity in physics, and we're still working with a lot of his results now, 100 years later, and making new discoveries like in the last 5 years that have to do with that. So that's kind of the big picture of gravity, very abstract. So we're going to first dive in with Newton. So as you recall, Newton was this brilliant guy. He did a ton in the fields of math, science, even philosophy. But one of the things, when you say Newton, everybody thinks of three laws of motion, right? Because that's what we first start teaching you about back in middle school. But one of his biggest contributions to physics is actually the work he did with gravity. And so when he was thinking about gravity and sort of trying to figure out is it a field force or not, what he started with, notoriously was thinking about an apple falling from a tree. But the thing he was really looking at was the Earth and the Moon. So if we have the Earth and we have the Moon, when Newton was alive, so this is around the year 1700 that he's doing this work. He was alive at a time when they were aware that the moon rotated around the Earth, right? So we know that it's going to run out of room on my board, but you know that the moon rotates around the Earth. And even back in his day when they didn't have the technology to be able to observe, astronomically, things that we do now, the moon you can see, right? Any night that it's clear, if the moon is out, it's pretty easy to find and identify. And so they were doing a lot of measuring with the moon, and so during his time, he would have known that the period of the rotation of the moon around the Earth was about 28 days, 27.3 days. That's about what they had it nailed down to then. And they can figure that out by observing the phases, right? That's the amount of time it takes to go through a cycle like full moon to full moon, new moon to new moon, so on and so forth. They also had a pretty good idea then there's a couple of methods you can use to measure distance, like astronomical distances. So distance of, for instance, the sun to the Earth or the Earth to the moon. And they're pretty heavy with vector algebra actually. And so back in his day, they had the approximate distance. It's still pretty good. between the Earth and the Moon of about 384,000 kilometers. And so he wanted to figure out the acceleration of the Moon towards the Earth, right? If the Moon is rotating in a relatively uniform circular motion around the Earth, so it maintains a constant speed, a pretty constant radius, so it's close to a circular orbit around the Earth, then the acceleration towards the Earth, of course the Moon's not coming in and bopping into us, but it has a centripetal acceleration towards the Earth because this is uniform circular motion. And so we say centripetal acceleration is equal to v squared divided by r, right? And so v for the Moon is 2 pi r over t because it's relatively uniform motion. And so if we put that in, I'm going to rewrite this as, maybe just to make it easier to see, 1 over r times v squared, okay? And then I'm going to put this quantity in for v and square it. So this becomes 1 over r times v squared, which is 4 pi squared r squared divided by t squared. So you see that one of the r's cancels out, right? And then we can plug our numbers in. Now we need to convert 27.3 days into seconds. And 384,000 kilometers, we want to write that in meters. So that would be 3.84 times 10 to the, let's see, this is fifth. So times 10 to the 8th meters. Okay, so when we plug those numbers in, just believe me because I adjusted it on my calculator and I'm getting lazy about writing. So when we convert, I'm going to write pi is 3.14. I'm going to convert the t from 27.3 days into seconds, and I put that r value in meters. I get a centripetal acceleration. It's actually quite small, 0.00272 meters per second squared. So I didn't do anything with gravity yet. All this was just totally review of uniform circular motion. So I'm treating the Moon as though it is an object uniformly rotating around the Earth. It pretty much is. And I'm finding its centripetal acceleration. So the value is 0.00272 meters per second squared. So back in his time, Newton had enough data to be able to figure out that acceleration. Now, here's where he starts to get into gravity. So I'm going to erase this. Legend has it, he's sitting and an apple fell at his feet. He's on the, campus where he worked in England. In his writing, he certainly refers to an apple. So he was comparing the acceleration of an apple towards the Earth to the acceleration of the Moon towards the Earth. Now again, because the Moon is actively orbiting, right, it's not going to like come crashing into Earth, but it is accelerating towards Earth. That's what binds it into its orbit. And so the apple's acceleration towards Earth, I'll say the acceleration of the apple, we know is approximately 9.8 meters per second squared towards the Earth. We always say it's negative because it's down, but it's towards the center of the Earth. And the acceleration of the Moon is 0.00272 meters per second squared. And so he said to himself, could these two accelerations be caused by the same thing, right? Because what is it that binds an apple to the Earth, or you or me to the Earth? As soon as we, if I'm at some height, let's say I'm on a chair, the moment I step off, boom, down I go, right? And I freely fall. An apple, the moment it separates a tree, boom, down it goes, and it freely falls. So could it be that whatever causes us to be bound towards the Earth is the same thing that causes the Moon to be bound towards the Earth? And we know, think about it intuitively, you already know. The answer is yes. Yes, it is. And so then he thought to himself, well, why? Why is the apple's acceleration towards the Earth so much bigger than the Moon's? And if we compare this, I'm just going to take 9.8 and I'm going to divide it by 0.00272, and I get about 3,600. So the apple's acceleration towards the Earth is about 3,600 times larger than the Moon's acceleration towards the Earth. And so if you're thinking, well, what's different about these things? Like, this thing's bigger, but it's got a much smaller acceleration. Well, the one thing that stands out is distance, right? The apple, it actually still has a distance away from Earth because it's being pulled towards the center. If you dig a hole, it's going to go to the bottom of the hole. If you dig it deeper, it'll keep going until it gets to the center where it would be stuck forever. That's a complicated problem for another day. But the apple's distance from the Earth is equal to the radius of the Earth, which is about 6.86, I think, times 10 to the 6 meters. The moon's distance from the center of the Earth is that radius I just gave you, about 3.84 times 10 to the 8th meters. And so if I look at these, it turns out that the moon is 60 times further away. And that's an interesting relationship. The moon is 60 times further away, and the apple has 3,600 times more acceleration. So, which mean force, right? And so 60, 3,600, what do we know about those? Well, one is the square of the other, right? If I take 60 squared, I end up with 3,600. And so this leads Newton to develop this relationship between distance and essentially the force of gravity. So he says, he first just essentially hypothesizes with this math, and then he uses some kind of complicated experimentation to get to his equation. But he says that the force of gravity depends on two different variables. It depends on mass and it depends on distance. So he thinks that it is directly proportional, and I'm going to say to the product of two masses, M1 and M2. Because in the case of the apple, this is a force of gravity between the apple and the Earth. Or in the case of the moon, between the moon and the Earth. So it's always, always, always between two objects. The force of gravity is always between two objects. So the force of gravity is directly proportional to their masses. The larger the mass of the object in question, the larger this force, right? The Earth can have a force that binds us to it, and I don't have that same force on you because of the Earth's mass. And then he says the force of gravity is inversely proportional to distance. The further away you are, the smaller this force of gravity is, right? So stars on the other side of the galaxy are not really influencing the Earth's motion in the same way the sun is. Why? They're a lot bigger. Some of them, I mean, you know, the sun's like a mediocre star. Why? Well, because of distance. So the closer things have a larger force. As R gets bigger, F gets smaller. So this is an inverse relationship. We call it R instead of D just because it would end up causing an orbit sometimes. And when we look at this, right, it's actually R squared. And that comes directly from this moon business. So the force of gravity is directly proportional to the product of the two masses and inversely proportional to the distance between, the square of the distance between the two objects. Now, Newton did some experimentation to actually put this into an equation. And so the actual equation is, I'm just looking for room on my little board. And I'll kind of talk about the experiment a little bit like when I see you in class on Wednesday. But the force of gravity is equal to big G, that's literally, we call it big G, times M1 times M2 divided by R squared. Big G is a gravitational constant. It just came out of experimentation. So just in the same way like pi is a constant, or when you're studying ideal gas laws, like R is a constant. This is just a constant. It's a really small number. 6.67 times 10 to the negative 11 newtons times meter squared per kilogram squared. Totally weird, like long-winded constant, but there it is. The thing to notice about this is it's very, very, very small, 10 to the negative 11. So to have a force of gravity that is not negligible, that's something measurable and noticeable, at least one of the masses has to be bigger than 10 to the 11th, right? So that's billions of kilograms. So people, we'll do a practice problem in the next PowerPoint or the next video. People don't have forces of gravity on each other. That's truly noticeable. So this is Newton's universal law of gravitation. In words, he says that every object in the universe with mass has a gravitational force on every other object in the universe with mass that's directly proportional to the product of their masses and inversely proportional to the square of the distance between them. And what's interesting about this force of gravity, this field force, is it can act across really large distances. So like sun, earth, that's a big distance. Center of the galaxy, there's a supermassive black hole. We're going to talk about black holes with this. We are bound to our galaxy by that thing. That's a huge distance. So it acts across really large distances. And the other thing that's unique about this force is it's always attractive. It never pushes apart. It's always pulling. So the force of gravity is always an attractive force. So in the next video, I'm going to do some practice problems with gravity.